Welcome to the first lesson of Unit 5. So just to give a brief background, make sure we remember how we got here. Unit 1, we constructed the idea of a limit in order to make sense of a function that was undefined at a certain point. We used the limit to define the instantaneous rate of change of a function, which we called the derivative. Unit 3, we wanted to find some rules for taking the derivative of a bunch of functions that we see very often. And so we used the limit definition to construct these derivative rules. And once we had these derivative rules, we could then take the derivative much more easily. And so we started looking at some applications of the derivative. How can we use the derivative to make sense of a situation? So Unit 4 was the first part of application of the derivative, and Unit 5 will be application of the derivative part 2. And what we're going to do in this unit is extend some of the ideas that we discussed in Unit 4 and also look at a couple of newer situations that will help us make more sense of real-world situations. This is going to be a very, very fun and interesting unit, and it's important that we remain firm in our understanding of the previous concepts of differentiation, because those are the concepts that are going to lead us to these slightly new methods of application. So today we're going to understand and employ something called implicit differentiation by applying the chain rule to implicitly defined functions. So notice that the chain rule is something we are already very familiar with, and really all implicit differentiation is applying the chain rule. Let's get started. All right, before we go ahead and get into implicit differentiation, I want to take a minute to kind of update some of the notation that's going to be used. So what we're familiar with using quite often, of course, is derivative notation. So if you have a function y, which is defined as f of x, then when you take the derivative of that, there are a couple ways to represent it. So you can say derivative of y with respect to x. Another way you can say that is y prime. And here I'm not writing the y prime of x. I'm not saying that it's a function of x. That's understood. So I just write y prime. And I could similarly say f prime of x, the derivative of f with respect to x. Those all work perfectly fine. And we've also seen second derivatives now. The second derivative of f with respect to x, which is, as you might assume, y double prime. And I can represent this in what's called Leibniz notation, so this is Newton notation. And Leibniz used dy over dx, the derivative of y with respect to x, the change in y with respect to x at any instant. And similarly, we can represent the second derivative as the second derivative of y with respect to x. Okay? And so often you'll be asked to find the second derivative of y with respect to x using Leibniz notation. Okay, now a couple more things here. So let's say I want to find the first, the value of the derivative at x equals 2. Okay, so you could say that. You could also say y prime of 2. And another way to represent this is dy dx when x equals 2. Okay? And so this is a way to say you're evaluating the derivative of y with respect to x when x equals 2. Okay? And as we'll see, we're going to use this notation a lot. And so sometimes you'll be asked to evaluate the derivative at a certain point. And this is how you represent that you're evaluating dy dx at a certain value. Okay, so with that in mind, that quick refresher, let's get into implicit differentiation. Okay, so let's go ahead and work through this discovery problem. You should go ahead and complete part A, B, and C on your own first, and get creative. Remember, we're just applying, my hint to you is we're just applying the chain rule, and when you graph this equation, you should use Wolfram alpha. Notice that when we're finding the derivative, dy over dx, what you're looking for is a function that gives you the slope at any point. Okay, so you can use the, what you looked at on the curve as a kind of a way to test whether you've done this correctly. And then once you've done that, we'll take a look, we'll talk about it together, and in doing so, we'll actually be defining the process of implicit differentiation. Okay, so here is the graph of all of these solutions to x squared plus y squared equals 1. This is the unit circle. It is a circle centered at the origin with radius of 1. And if you take a look at this graph, you'll notice a couple of things. The first is that this is not a function, right? It doesn't pass the vertical line test. For each x value, there's not one unique y value. So you can't solve this equation explicitly for y. You can't have y equals just, this one rule and have it define a specific value given an x value, right? If your x value is 0.5, there are two possible y values that you could have. So that makes this equation look a little different, and it will definitely make the way we take the derivative a little bit different, but that doesn't change the fact that at any point along our curve, there's still an instantaneous rate of change. There's still a tangent to the curve at any point. And so in the first quadrant, it just sort of seems to make sense that I might pick a point right here. And at that point right there, there certainly is a tangent to the curve, right? And so there should be a derivative at this point. In other words, I should be able to find the derivative of y with respect to x. This line here has a slope, certainly does. And I should be able to write the equation of this tangent line. Now, before we do that, as we've done in the past, I want us to consider what we'd expect when we find the derivative of y with respect to x. So at this particular point here, I know that my y value and my x value, my x value and my y value are both positive. Okay, this point has a positive x and a positive y. But the slope at this particular point is negative. So when I get my derivative of y with respect to x, I should have something that gives me, when I have a positive x and a positive y, gives me a negative value because my derivative is the slope, and this is clearly a negative slope. So with that in mind, I'm now going to find the derivative of y with respect to x using the equation here, knowing that when I get, I can, whatever I get, I can sort of test back with this particular case here. So I have x squared plus y squared equals 1. Now, how am I going to find the derivative of y with respect to x? Well, probably the first thing that you tried is to say, okay, I don't have y solved for, but if I solve for y, then I could take the derivative of both sides, and I'd have dy dx is equal to whatever the derivative of the right side is. Okay, sure, let's do that. So I'm going to solve for y. I'm going to get 1 minus x squared. And now here's the problem. We talked about this a second ago, which is that this is not a function. In other words, there's no clearly defined rule that if I give you an x value, this is what the y value is going to be. Notice that there are 2 for each x value. And we see that because when we take the square root of both sides, notice that y squared, well, it's always going to be positive. So it doesn't matter whether y is a negative value, in other words, when we square root this, whether we take the positive value of that square root or the negative value of that square root. Y is equal to the square root of 1 minus x squared, but it's also equal to, and y is equal to negative square root of 1 minus x squared. And I can see pretty clearly why I need 2 equations. The first equation here says for any x value, what is the y value? And it's going to be positive, meaning I'm looking at all the positive y values. And this equation here says for any x value, I'm going to give you the y value that's negative. Right? I have a negative out front. And that gives you all the negative y values. So what I could do at this point is, I could take the derivative of this function, and that would give me the slope at any instant above the x-axis. And I could take the derivative of this function, and that would give me the slope at any point that, along the circle that's below the x-axis. And I encourage you to actually go ahead and pause and try that on your own and corroborate that that makes sense for a couple of points. But I'm fully in belief that that will work. And so what I want to do now is move on and think about a way that I could find a derivative, dy dx, that will allow me to compute the slope at any point around my circle without the need for two separate equations. All right. So I'm going to start off in much the same fashion that we just did, which is I have this equation, and notice that this equation cannot be solved, I cannot explicitly solve for y. If I tried to, I would get two separate equations. So what I have to do is notice that y is implicitly a function of x, meaning that even though I can't write it out, there is a relationship between y and x. Y is a function of x. It's just that I can't write it out in some nice, neat way. So I start with this assumption. I assume, correctly of course, that y is a function of x, meaning y is equal to some function of x. Okay? And now with this in mind, I'm going to take the derivative of both sides of my function. Okay, so I'm going to apply my derivative operator to the left side and take the derivative of the right side. Now notice I'm taking the derivative, I want the derivative with respect to x, so I'm taking the derivative with respect to x of both sides. All right, so I'm taking the derivative of both sides. Now the right side is very simple. The derivative of 1 with respect to x, the derivative of any constant with respect to x is 0 because this value 1 doesn't depend on x. This equals 0. And the left side, I can use the sum rule. So the derivative of a sum is the sum of the derivatives. So this left side will be the derivative with respect to x of x squared plus the derivative with respect to x of y squared. All right. So now we're in business. We can take the derivative with respect to x of x squared, no problem. That's just going to be 2x to the first power, or 2x. What about the derivative with respect to x of y squared? So at first glance, you're like, well, there's no x value involved here, so maybe this is a constant. The derivative of a constant is 0. Close, but not quite. Remember, y is a function of x. And this means that the derivative of y with respect to x, or dy dx, is just the derivative of this function, f prime of x. But notice we're not taking just the derivative of y, we're taking the derivative of y squared. So if I'm assuming that y is a function of x, well that means y squared is whatever this function of x is squared. So when I take the derivative with respect to x of both sides of this function, notice that I need to use the chain rule here. I have some function of x being squared, and so I have to take the derivative of the outside, which is squaring whatever this function is, and then the derivative of the inside. So when I take the derivative of this, I'll end up with 2 times f of x times the derivative of f of x. Okay, well, remember, f of x is just whatever my y value is. That's the function that gives me y. So when I take the derivative of y squared, I'm thinking of this y as this function of x, so I need to use the chain rule. So the derivative of this is going to be 2 times y times the derivative of whatever y is with respect to x. So writing this out, I have 2 times y, the derivative of the outside function, which is squaring y, times the derivative of y with respect to x. All I've done is rewrite this right side where I'm thinking of y as this function of x. And that is what we're doing here. When we write y, we are thinking of it as a function of x. And so when we take the derivative of y squared, we have to use the chain rule because this y represents a function of x. And so following the chain rule, we take the derivative of the outside, which is squaring y. And so the derivative of y squared, following the power rule, is 2y. And employing the chain rule, because we still have to take the derivative of the inside function, times dy dx, or the derivative of y with respect to x. Now notice that this is actually the value we're trying to find. And so since we have this now in an equation, we can actually isolate this value, this rate of change, dy dx, and we'll have then an expression for the derivative of y with respect to x. So if I subtract 2x from both sides and then divide by 2y, I'll be able to solve for dy dx. So go ahead and do that now. Okay, so when you do that, subtracting 2x from both sides and then dividing by 2y, the 2's will cancel, and I'll be left with an expression, or in other words, actually an equation for the derivative of y with respect to x, which is that the derivative of y with respect to x at any point, which has an x and a y value, is negative x over y. So there's a couple of interesting things to note here. The derivative of at any point, or the slope at any point, is actually a function of both x and y. And that should make sense because this is only one function. And so the way in which I need to define a point is actually by giving you both the x and the y value, because I can't just give you the x value because there are two corresponding y values. So in order to define the slope for a unique point, I actually need both the x and the y value. And this is a very important piece because now I can actually say, okay, what's the slope at this particular point? And so this particular point, this might be square root of 2 over 2, comma, square root of 2 over 2. Okay? And I could find the slope at this particular point utilizing my equation. So the derivative, let's actually do that. The derivative of y with respect to x, and here I'm going to use my new notation, and it's at the point square root of 2 over 2, comma, square root of 2 over 2. Well, that's equal to, and so my x value is the square root of 2 over 2, my y value is the square root of 2 over 2, so it's something over itself, that's going to be 1, and times a negative is just going to be negative 1. And that sure makes sense, right? This looks like a line that has a slope of negative 1. And so we can use implicit differentiation to take the derivative of functions when we can't solve for y. So we treat y as a function of x, and then we differentiate using the rules that we've set out, most importantly the chain rule. So the big step here was noticing y is a function of x, so when I differentiate with respect to x, I have to treat this y value as a function of x. So I take the derivative of the outside, which is taking this function of x and squaring it. So I take 2y to the first power, and then the derivative of the inside, which is the derivative of y with respect to x. Then I can solve for this derivative of y with respect to x, and I'm going to get a function in terms of both x and y. And that's okay, because at any given point where I know the x and the y value, I can then find the slope at that particular point. And we did that here. So let's go ahead and make a very clear now step-by-step process for how we actually take the derivative of y with respect to x of a function like this where y is implicitly defined. All right, so if I'm given a function where y is not explicitly solved for, meaning it's not, y equals 3x plus 2, right? Where y is instead implicitly defined as a function of x, so we can't actually solve for it, then we can still find the derivative of y with respect to x using the implicit differentiation process. So we differentiate both sides of the equation with respect to x. Don't forget to use the necessary rules of differentiation. You can't let those fly away. collect terms with a dy dx on one side of the equation. Then we want to factor out that dy dx so we can solve for it, and then we have our equation for the derivative of y with respect to x. A couple of things to note. The first is that this derivative that we get is probably going to be in terms of both y and x. You're going to need both the y and the x values to find the derivative at that point, and that's perfectly fine. The other big thing is that we can't forget that we're finding the derivative, and the derivative is the slope at a given point. And so looking at this graphically can often be very helpful. Now, you can't graph, your calculators can't graph an implicitly defined function. It needs you to define y explicitly. But Wolfram Alpha certainly can. So take advantage of this to get some intuition and confirm your solutions early on, and so that you feel really comfortable with what you're doing. Let's go ahead and do this example quickly. Go ahead and try it first on your own. Take a couple of minutes, and then we'll go through it quickly and then move on to some more interesting examples. All right, so I'm going to follow my process here. I have y defined implicitly. I haven't solved for y, and so I'm going to use implicit differentiation. I'm going to differentiate with respect to x on both sides. Now, the derivative of x with respect to x, very simple. Using the power rule, I get 1. And the derivative of y squared with respect to x, and remember, we are thinking of y as a function of x. So when we take this derivative, we need to use the chain rule, and that's going to be 2y dy dx. All right. Now, I want to collect the terms with dy dx on one side of the equation, and I've done that here, so step 2 has been accomplished. And I also want to factor out dy dx. Well, I have done that, right? I have written this in terms of 2 factors, 2y times dy dx. That's perfectly fine. So I've accomplished step 3 as well, and now I want to solve for dy dx by dividing on both sides. So I have dy dx is equal to 1 over 2y. And this is my derivative. Now, there are a couple things to notice. You found the derivative of y with respect to x, and there's no x involved. And that feels a little weird. But if we look at the graph, you'll actually see that this is perfectly fine. So I'm going to pull up the graph here in a second, but notice just further that if I want to define the slope at any point on this curve, I simply need the y value of that point, which is interesting and actually very useful. Let's take a look. So here's the curve that I get when I graph y squared equals x. Notice I didn't use the word function. It's not a function. So let's say that I want to find the instantaneous rate of change, or the slope, when y is equal to 1. Well, when y is equal to 1, I'm at this point over here. Notice I don't care what the x value is. Okay, it turns out that the x value is also going to be 1, because 1 squared is 1. And the slope of this tangent line is going to be given by dy dx evaluated at y equals 1. And that is going to be 1 over 2 times 1, or 1/2. And I can do the same if y was negative 1. So when y is negative 1, I'm at this point here. I can look at the slope of the tangent there. The slope of that tangent is going to be given by the derivative of y with respect to x evaluated at a y value of negative 1. And there I have 1 over 2 times negative 1, which will be negative 1/2. Which also makes sense because this clearly is a negative slope, and this clearly is a positive slope. All right, I'm going to do 2 more examples that implement a little more complex implicit differentiation and combine them with some topics that we've already seen. If you're looking for a couple more examples, there's 2 on page 165 that would be helpful, certainly to look at if you're looking for a couple more simple examples, but we're going to move on now. All right, so for both of the problems that we're going to do, you should try these first on your own. Read through the problem carefully, make sure you know what you're trying to find, have a plan for how you're going to find it before you jump in so that you're not getting confused and lost along the way. And once you've done that, go ahead and press play and we'll take a look at the solutions. All right, I want to write the equation for the tangent and the normal to the ellipse, and this is the equation that gives me the ellipse at the point -1, 2. So I'm not going to go to Wolfram Alpha and look at the graph because that's not something I'll have on the AP test, and we don't need it. An ellipse, what does that look like? Well, maybe it looks something like that. That's pretty awful, but you get the idea. And so at the point -1, 2, maybe that's over here. I want to find the tangent and the normal line. So the tangent and the normal. All right, so what I need clearly is I need the derivative of y with respect to x at this point, -1, 2. So I'm going to need to find the derivative, and then I'm going to need to evaluate it at -1, 2, and then write my equations. So let's go ahead and get started. First, I'm going to find the derivative. So I'm going to need to use implicit differentiation here to find the derivative. So to find dy dx, I'm going to follow my process. So the first thing I'm going to do, I'm going to take the derivative with respect to x of both sides. And now I can, on the right side, take the derivative very easily. That's 0. And on the left side, I'm going to break this derivative up and take the derivative of x squared minus the derivative of x times y plus the derivative of y squared. All right, so the derivative of x squared, that's simple enough. Using the power rule, I get 2x. Now, here I have the derivative of x times y minus. I should put that up front. So the derivative of x times y. Now, this is a product of two functions of x, right? Y itself is a function of x. So I'm going to use the product rule here. Now, what I recommend is actually going off to the side and finding this derivative without doing it inside the equation. That way when you come back, it'll be nice and neat. So let's go ahead and go off to the side real quick. So I have the derivative with respect to x of x times y. And remember, y is a function of x. Right? We're treating this as a function of x. So I'm going to apply the product rule. So what I'm going to do is I'm going to first take the derivative of the first function times the second. So the derivative of x is 1 times y plus the first function, x, times the derivative of the second function. Well, the derivative of y is just the derivative of y with respect to x. Notice, of course, that there's no need. I'm using the chain rule here because I'm thinking of this just being y to the first power. So there's no outside function here. This is just y, which is a function of x. And so the derivative of y with respect to x is just the derivative of y with respect to x, whatever that is. So I have y plus x dy dx. All right, so I'm going to go ahead and put that in. I need that in parentheses. Y plus x dy dx plus the derivative with respect to x of y squared. And we've done this before, right? This is a function of x, so when I'm squaring a function of x and taking the derivative, I take the derivative of the outside times the derivative of the inside. And the inside function is y, so the derivative of y with respect to x. And that equals 0. All right, at this point, I need to get all of my terms with dy dx onto one side, all the other terms on the other, and then I need to factor out a dy dx. So notice I need to apply this negative sign to both of these, so this will be negative y, and this will be negative x dy dx. And so then I'm going to subtract a 2x and add a y to both sides. So notice that's what I've done here. I've subtracted 2x and added y, because I had a negative y here, and I'm left with negative x dy dx plus 2y dy dx. I factor out this derivative of y with respect to x, and I'm left with dy dx times 2y minus x. I just rearranged the terms, and over here I rearranged the terms as well. I have y minus 2x. I can now divide to solve for dy dx. So dividing both sides by 2y minus x gives me my derivative of y with respect to x. So that's what I was trying to find there, and now I know I want the tangent to the curve at negative 1 comma 2, so I need dy dx evaluated at this point, negative 1 comma 2. That'll give me the slope, and then I'm going to find the reciprocal, the opposite reciprocal, in order to write my tangent. All right, so we have our derivative, and we now want to find the slope at the point negative 1 comma 2, and so that will give us the slope of the tangent. So I want to take my derivative dy dx, and I want to evaluate it at the point negative 1 comma 2. So here my x value is negative 1, and my y value is 2, and so I'm going to substitute that into my equation here. And after substituting and solving, I get 4/5, and so that is the slope of the tangent. And so now I can write my equation for the tangent. I know that the point it goes through is negative 1 comma 2. So the tangent at negative 1 comma 2 is going to be y minus 2 equals 4/5 times x plus 1, and the normal at this same point is going to be y minus 2 is equal to negative 5/4 opposite reciprocal times x plus 1. And you could, of course, rewrite these equations so that they are in slope-intercept form, but these will do just fine. And so those are the tangent and the normal to my ellipse at this particular point, negative 1 comma 2. Okay, so here we want to find the second derivative, and we are given the first derivative. So you want to think to yourself, the process that has gone through. It looks as though implicit differentiation got you to dy dx. And now we're going to try and take the derivative of this again to get the second derivative. So go ahead and try that on your own first, and then we'll take a look. All right, so I know that the second derivative is the derivative of the first derivative. So what I'm going to do is I'm going to take the derivative of both sides with respect to x. So I have the derivative of dy dx, and that is equal to the derivative with respect to x of this whole function, 1 plus sine of y. All right, now the derivative of the first derivative is just exactly that. It's the second derivative, right? And now I need to take the derivative of this here, and so I'm going to use the sum rule. So the derivative of 1, I know what that is, and then I'm going to take the derivative of the sine of y with respect to x. Okay, so the second derivative of y with respect to x, the derivative with respect to x of 1 is 0, plus the derivative with respect to x of sine of y. Now, y is a function of x, so remember the derivative of sine of u, where u is a function of x, is the cosine of u times the derivative of u, right? And so here I have this function of x, which is y. Remember, it's implicitly defined. We're assuming y is a function of x. So the derivative of sine of y with respect to y, right, the derivative of the outside function, is simply going to be cosine of y. But this is the derivative with respect to y, right, in terms of y. I need to take the derivative of y with respect to x. So I'm going to multiply by the derivative of y with respect to x, right? The derivative of this interior function, which is y. And the derivative of y with respect to x is just that, derivative of y with respect to x. Okay? Notice this wasn't y squared, so I didn't have to do 2y times derivative of y with respect to x, because this is just y to the first power, right? So now I have an equation for the second derivative, but notice that it is in terms of the first derivative. Well, that's weird. I'd like to just be able to compute the second derivative by plugging in values of x and y. But notice we know what the first derivative is in terms of y, so I can plug that in here. So this is going to be equal to cosine of y times the derivative of y with respect to x, which is exactly 1 plus sine of y. All right? And so this is the second derivative. And if I wanted to, I could multiply this in to be cosine y plus cosine y times sine y. And this would be the second derivative of y with respect to x. Okay? So the key step here was making the substitution where we already know the first derivative. So when we compute the second derivative using implicit differentiation, we have to make sure we substitute in the value of the first derivative. So if I go back to the notes I took on the process of implicit differentiation, I want to make note that when I'm finding the second derivative, I will need to make a second differentiation where I actually take the derivative of the first derivative. And when I differentiate that implicitly, I will need to make sure I substitute back in the value I found for dy dx, right? Because I'm solving for the second derivative, so I need to actually have this defined already, and that is either defined for us as it is here, or we've actually already found it in the first part of the problem. There are a couple things that I want to bring to your attention before you move on to the homework. And the first thing is that if you want to see another example of finding the second derivative, if you go to page 167 in the book, there is an example there. And secondly is that using the notation dy dx is very common, but equally as common is representing this as simply y prime. So another way that this might be written is, and I'm talking about this portion here, so if I have cosine of y times the derivative of this inside, right? So the derivative of y with respect to x, and another way of writing that is, as we've spoken about before, y prime. Okay, so this means the same thing as dy dx, and similarly I could write y double prime for the second derivative. Okay, so make sure that if you see, if someone's asking you for y prime, that's perfectly fine. You're still finding the derivative, and you can still differentiate implicitly, use implicit differentiation. And of course, you can represent dy dx as y prime, where I haven't written the x there, but it's understood. Okay? So at this point, go ahead and move on to the homework 5.01, and make sure that you are giving full effort.